right, so we've seen that we measure pressure of gas traditionally using heights of columns of mercury, in terms of heights of mercury columns. Now, those are atmosphere and torr and millimeter mercury and centimeters mercury. Those are not SI units. So let's try to relate it to SI units, since the preferred units these days are SI units. Okay, and the way to do that is we need to understand exactly what does pressure mean. Pressure is actually defined as force per unit area. So if you have like a barometer, okay, and your air is supporting a column of mercury. So your air right here is supporting a column of mercury that is 76 centimeters high. What's actually happening there is that at this level right here, the pressure of the air is equal to the pressure due to that column of liquid. Okay, pressure is just the force that, if let's say you were down here, okay, at this level, the force that you would feel per unit area, that's pressure that you'd feel at this point, at this level, would be the same as the pressure that the air exerts at that point is the same as the pressure that the column of mercury is exerting at that point. Okay, so let's try to derive what the pressure due to this column is in terms of SI units. That way we can have a relationship between 76 centimeters of mercury and the SI units. Okay, so what's our definition of pressure? It's force per unit area, right? But the force that you would feel at this point right here, oops, sorry. Okay, so here's your column of mercury, right? The force you would feel, so this is 76 centimeters. The force you would feel over here would be the weight of this column divided by the cross-sectional area. So the weight of the mercury above you divided by the area of that column. Okay, so you have a cross-sectional area. It can be a cylindrical column, or it can be a square column. It's usually cylindrical. Okay, it doesn't matter. Now, the weight, okay, so what's weight? If you recall, it's mass times acceleration due to gravity, right? mg. And the unit for that is SI unit for that is kilograms times meters per second squared, right? The force on an object by Earth's the gravitational force on an object is equal to the mass of the object times acceleration of the object due to the pull of gravity. Mass times acceleration, so kilogram meters per second squared. So this is mg divided by the area. Okay? But mercury is a liquid that has a density, known density of 13.6 grams per cubic centimeter, or 13.6 times 10 to the third kilograms per cubic meter. So here's a nice thing to remember. If you have your density in grams per mil or grams per cubic centimeter, to change that to SI units, which would be kilogram per cubic meters, okay, just multiply by 1,000. Okay, so the density of water is 1 gram per mil. In SI, it says 1,000 kilograms per cubic meter. This is mercury is 13.6 times more dense than water. Okay, now if your mass, if you know the density and the volume of your liquid, density, if you recall, is mass over volume, right? So if I know the density, I can figure out the mass by just multiplying the density by the volume. So mass is just density times volume, right? Density, multiply both sides of this equation by V, you get density times volume equals mass. So I can rewrite this expression as density times volume times G divided by the area. What I've done is I've replaced the mass by density times volume. Okay. Now, what's the volume of a cylinder? Let's imagine this is a cylinder with cross-sectional area A and height h. Volume of the cylinder is equal to the area of the cross-sectional area multiplied by h. So instead of volume here, I can write area, cross-sectional area times h, and then G is over here, and then I have A down here. Okay? So now, what I can do is A cancels out. I have a formula for a pressure due to a column of liquid. It's just equal to density times the height of the liquid times acceleration due to gravity. And so let's apply that for mercury here. So pressure due to a column of mercury is 76 centimeters high. So 76.0 centimeters of mercury would be equal to, okay, the known density of mercury, which is 13.6 times 10 to the third kilograms per cubic meter. The height of our mercury column is 76 centimeters, so 76.0 times 10 to the negative 2 meters. Okay? And acceleration due to gravity is 9.81 meters per second squared. Okay? So let's go ahead and calculate that. You get 13.6 times 10 to the third times 76 times 10 to the negative 2 times 9.81. That gives me 101,396. So I'll put that in scientific notation. 1.01, 3 sig figs. I only have 3 sig figs here. Times 10 to the fifth. And my unit is, what should be my unit? It should be kilogram per second squared, and my meter here, that's meter squared, will cancel 2 of the meters down here. That leaves you a meter there. So kilogram per meter per second squared. Now that's kind of hard to remember, so we give that a special name. We call that a Pascal. Okay, so Pascal is the unit of pressure in SI. So 1.01 times 10 to the fifth Pascal. Now, you'll notice that you should be able to show that this is equivalent to a Newton per square meter. A unit of force, if you recall, a Newton is a unit of force, and per square meter is a unit of area, right? And that's a unit of force. Unit is Newton, and a Pascal is also a Newton per square meter. And if you break this down into its base units, you'll find both of these are going to be, this is going to be equal to kilogram per meter per second squared. Now, the more precise value is 1 point. If we were to use more accurate, more precise values for our density of our mercury and acceleration due to gravity, then you can see that 76 centimeters, okay, of mercury, which is 1 atmosphere, right? We defined that earlier to be 1 atmosphere, is equivalent to 1.01325 times 10 to the fifth Pascal. Okay, so that's a conversion factor that you can use, conversion equivalent that you can use to convert units from SI to the more traditional ones, torr, atmosphere, and millimeters of mercury. Okay, so 1 Pascal is equivalent to a Newton per square meter. That's the SI unit for pressure. And 1 atmosphere is defined to be exactly, I'm not sure if it's exact, but it's to be very precisely to 1.01325 times 10 to the fifth Pascal. Of course, you know, 1 atmosphere is 760 torr, and a torr is a millimeter of mercury, so that's also 760 millimeters of mercury, and that's 76 centimeters of mercury. Newer units that have been recently defined is the bar. A bar is defined to be 1,000 millibars, and it's just defined to be 10 to the fifth Pascal. Okay, so 1 atmosphere, which is 1.01 Pascal approximately, is times 10 to the fifth. Okay, Pascal is equal to 1.01 bar. Okay, so anytime you see bar, that means 10 to the fifth Pascal. You can see that a bar, the reason a bar was invented is you can see that a bar and an atmosphere are almost the same. They're about 1% there's about 1% difference. Okay, and the nice thing about the bar is it's just a power of 10 times a Pascal, 10 to the fifth Pascal. So it's a lot closer to SI, you might say. All right.